What specific problem does the chain of draft (COD) method aim to solve in the context of reasoning models, and how does it differ from existing approaches like chain of thought (COT)?
The chain of draft (COD) method aims to address the problem of excessive verbosity and high computational costs associated with existing reasoning models, particularly those using the chain of thought (COT) approach. While COT encourages detailed, step-by-step reasoning, it often results in lengthy outputs that consume a significant number of tokens and increase latency. In contrast, COD prioritizes efficiency by promoting concise, dense information outputs at each reasoning step, limiting the number of words to essential calculations or transformations. This minimalist approach not only reduces token usage by approximately 80% in arithmetic reasoning tasks, but also maintains or even improves accuracy compared to COT. Ultimately, COD aligns more closely with human cognitive processes, allowing for more practical applications of large language models in real-world scenarios.
How does the proposed method, chain of draft, work? Illustrate step-by-step its mechanisms and processes, highlighting any novel components introduced in the methodology.
The proposed method, chain of draft, COD, operates by encouraging large language models, LLMs, to generate concise outputs at each reasoning step, mimicking human cognitive processes. Instead of verbose intermediate reasoning typical of chain of thought, COT, COD limits each reasoning step to a maximum of 5 words, focusing solely on essential calculations or transformations needed to progress toward the solution. This minimalist approach not only reduces token usage significantly, by about 80%, but also cuts down latency by up to 76.2% compared to COT. COD maintains accuracy, achieving 91% in arithmetic reasoning tasks while requiring far fewer tokens than COT, which often generates around 200 tokens per response. The methodology's novel component lies in its emphasis on minimal drafts, allowing LLMs to produce dense information outputs that enhance efficiency without sacrificing correctness or transparency in the reasoning process.
Can you provide a detailed illustrative example of how chain of draft operates? Walk through an example similar to the arithmetic problem presented in the paper, explaining each step of the algorithm.
To illustrate how chain of draft COD operates, consider the arithmetic problem. Jason had 20 lollipops. He gave Denny some lollipops. Now Jason has 12 lollipops. How many lollipops did Jason give to Denny? In a standard prompting approach, the model might directly output the answer without showing any reasoning, which lacks transparency. The chain of thought COT method would provide a detailed reasoning process, but would be verbose, inflating token usage. In contrast, COD condenses the reasoning into minimal, essential steps. For this problem, COD would generate a concise equation: 20x equals 12, x equals 20 to 12 equals 8. Here, the reasoning is distilled to the critical mathematical operation needed to find the solution, focusing solely on the necessary calculations while omitting irrelevant contextual details. This results in a significant reduction in token count and latency, demonstrating COD's efficiency while maintaining correctness and transparency in the reasoning process.
What are the theoretical or practical benefits of using chain of draft compared to standard chain of thought prompting? Discuss improvements in efficiency, accuracy, and usability in real-world applications.
The chain of draft COD approach offers significant theoretical and practical benefits over the standard chain of thought COT prompting. Firstly, COD enhances efficiency by reducing the average output token count by approximately 80% and cutting latency by up to 76.2% for models like GPT-4o, making it more suitable for cost-sensitive and latency-sensitive applications. In terms of accuracy, COD maintains a high performance level, achieving 91% accuracy in arithmetic reasoning, which is only slightly lower than COT's 95%, while still providing concise outputs. Additionally, COD's minimalist approach aligns more closely with human reasoning processes, improving usability in real-world scenarios where concise communication is essential. Overall, COD not only streamlines the reasoning process, but also ensures that LLMs remain practical and effective for diverse applications.
How was the effectiveness of chain of draft validated or tested? What experimental design, datasets, metrics, and benchmarks were used to demonstrate its performance?
The effectiveness of chain of draft, COD, was validated through empirical experiments across 3 categories of reasoning tasks: arithmetic reasoning, common sense reasoning, and symbolic reasoning. The primary dataset used for arithmetic reasoning was GSM-8K, which consists of 8,500 diverse grade school-level mathematical problems, while common sense reasoning was evaluated using tasks from Big Bench, specifically date understanding and sports understanding. The experimental design involved comparing COD against 2 other prompting strategies, chain of thought, COT, and standard prompting, with metrics focusing on accuracy, token usage, and latency. Results showed that COD achieved 91% accuracy in arithmetic reasoning, with only 40 tokens per response, significantly reducing token count by 80% and latency by up to 76.2% compared to COT, which had over 95% accuracy but used approximately 200 tokens. Additionally, COD outperformed COT in common sense reasoning tasks, demonstrating its efficiency and effectiveness across various benchmarks.
What specific results were achieved by implementing chain of draft across the various reasoning benchmarks? Include comparisons of accuracy, token usage, and latency against the chain of thought and standard prompting approaches.
The implementation of chain of draft, COD, across various reasoning benchmarks yielded significant improvements in accuracy, token usage, and latency compared to both chain of thought, COT, and standard prompting approaches. In arithmetic reasoning using the GSM-8K dataset, COD achieved an accuracy of 91% while requiring only about 40 tokens per response, which is a reduction of 80% in token count compared to COT, which generated approximately 200 tokens per response. For common sense reasoning tasks, COD not only reduced the average output tokens from 189.4 to 14.3, a 92.4% reduction, but also outperformed COT in accuracy in several cases. In symbolic reasoning, both COD and COT achieved perfect accuracy of 100%, but COD still demonstrated a significant reduction in token usage, with reductions of 68% for GPT-4o and 86% for Claude 3.5 Sonnet compared to COT. Overall, COD effectively maintained or improved accuracy while drastically reducing both latency and computational costs.